Okay, now, believe it or not, we did all the heavy lifting. So let me change the colors one more time. The nice thing about using this way, this critical value technique, is that if you've already done the critical value and you're asked to find p-values, it's very simple. Okay? Remember, all the p-value is, where's my pen? All the p-value is it's the probability that you end up with a score at least that extreme, that your test statistic is going to be at least that extreme. I'm actually going to use this because this goes out to hundreds, which is how my chart works. So watch. If I go to my chart and I got a negative 1.62, so negative 1.62 is right there. Look at what my p-value is. So if I go back here, let's see, z equals negative 1.62 implies that my p-value is equal to, what was that, 0.0526? Is equal to 0.0526. Since 0.0526 is greater than 0.05, just barely, just by the skin of our teeth. Do not reject the null hypothesis. There is not enough evidence to reject the claim that an average of 30 pounds a week of garbage is produced by a certain community. All right? Okay, now, God, I don't even want to think about what happens if I try. Let's see if I can find that where we wrote down all of our null and alternative hypotheses. There they were. Okay, remember this guy? Human body temp is 98.6 degrees Fahrenheit. So this is, notice that is equals, right? So I'm either going to be equal to or I'm going to be not equal to. That's the way to think about that. Now I'm going to go back here and let's do a hypothesis test on it. All right, let's see what we can figure out. I'm going to go, let's go, whoa, easy. I'm spazzing, sorry. Okay, here it is. And I'm going to go over to the next page. And we know that the null hypothesis, let's stay with green, is 98.6. The alternative hypothesis is mu is not equal to 98.6. And let's go out and gather some data. All right, let's say that our data was, we took 106 body temperatures, and we ended up with a mean of 98.2. Again, your spidey sense may be tingling. It's less than. Is it enough? I don't know what's going on. Let's assume that the standard deviation from prior information is 0.62. Okay? Okay, so let's get after it. Let's go ahead and do the critical value way first. Nothing to it. So we'll go over here. I'm going to draw my curve. All right, here we go. We know sample means distribute themselves normally. If I put 98.6 here, but I know that my test statistic is going to turn it into a 0, right? All right, let's see, not equal to. Okay, now how does this work again? Well, let's just for giggles, let's pick alpha equals 0.05, which means I got to split the difference because I can miss in either direction. This is going to be 0.025. Think about alpha as being the amount that you can miss by, and this is going to be 0.025. Remember, both of these are really just alpha halves. Okay? Now we got to figure out our critical values. So I'm going to figure out my critical value, and we'll write that down right directly on our work. Once you've done a few of these, they go really quick. It's surprising how quickly they go. So let's stumble over this away. What am I looking for? 0.025. Oh, look at that. I nailed it. Negative 1.96. And if it's negative 1.96, we know by the symmetric property of the normal distribution, then it's going to be positive 1.96 as well. Does everybody see where I got that? Where was that? 0.025. I got myself lost. There we go. Negative 1.96. So if I stumble back here, I know that this critical value is going to be, I'm going to open this thing up. This critical value is going to be negative 1.96, and this critical value is going to be a positive 1.96. And then all I'm going to do is take my test statistic, which is z, and if it ends up in either one of these critical regions, I get to reject the null hypothesis. If it doesn't, then I don't. Okay? All right, so, excuse me, check it out. What is Z? I'm going to do 98.2 minus 98.6 divided by 0.62 divided by the square root of 106. All right? So I'm definitely we're playing ball on the left-hand side because clearly my mean was less than 98.6, right? So what is that? Excuse me, negative 0.4 divided by prin 0.62. Respect your prins on these too. You should respect your negatives, but you should also respect your prins because they can really screw you up if you're not careful. 106 and prin. And holy goodness gracious, negative 6.64. Now, that's a huge number. Let's go back and double check that. So 90, whenever I get a number that's so big, let's see, 98.2 minus 98.6. I hit the brakes, I relax, and I calm down and put some information in here. So standard deviation was definitely 0.62 divided by second square root. When in doubt, you can't be too cautious, right? N equals 106. And yep, negative 6.64. So what do I do? Well, if the critical value is negative 1.96, negative 6.64 is like over here. This is like Z equals negative 6.64. All right? Okay, now I'm going to show you a little trick here when we get to the p-scores, but for now, just look at it. It's real simple to tell. All right? Since Z equals negative 6.64 is in the critical region, we reject, being interesting little dingy dingy. Let's see, we reject the null hypothesis. It appears the average body temp is less than 98.6. Now, the way to sort of lawyer up on this is instead of it appears, what we would say is there is evidence. And there is. Remember, as long as this, we knew sigma, and as long as this was a randomly selected sample. In other words, if these dudes just poured out of a day of snowboarding and we took their, or ladies, sorry, I don't mean to be gender biased, and we took their temperatures and they got an average of 98.2, that's not very random. So there is evidence. That's another way to say it. Okay? Now, this can be really confusing for students when they try to do p-value because negative 6.64 is such a big number. And if I stumble back over here, let's do p-value over here. Now, look at this. The smallest, the most negative that we can go, according to this, is negative 3.49. All right? Which gives me a p-value of 0.0002. So when we're dealing with charts, now your calculator is actually going to spit out a number. It'll give you a value of like 0.000001 or something like that because the computer can do those things. But when you're dealing with charts, the best that we can do is, if I go back here, when I write this up, since Z equals negative 6.64, this implies that the p-value is, and remember I'm using a chart, that's all I have, is less than 0.0002. I'm going to go up this way, you guys, bear with me. 0.000002 is clearly less than. Now here's the tricky part. Remember this? Since we're two-tailed, we have to talk about alpha divided by 2. So 0.05 divided by 2, which we know is 0.025. In this case, it doesn't matter. It could be alpha divided by 10, be alpha divided by 100, and we're still going to be less than this. Okay, remember, when you've got two tails and you're doing p-values, you have to divide alpha in half because you can miss on both sides. I'm going to scream and yell and wave my arms and get funky with that. Okay? 0.0002 is less than 0.025. This implies we have evidence It sounds a little more scholarly. To reject the null hypothesis. All right. Hey, I hope that was helpful. I know that I don't do a whole ton of examples, but these examples are going to be useful. Now, I'm hoping that there's a nagging question in the back of your head that says, well, what happens if we don't know sigma? Well, we've already played with this with confidence intervals. I'm going to do 2 more examples that deal with this kind of a problem where we don't know what sigma is. Okay? So bear with me, and I'll see you in the next little module.